Welcome to FYI, the For-Your Innovation podcast. This show offers an intellectual discussion on technologically enabled disruption, because investing in innovation starts with understanding it. To learn more, visit arc-invest.com.
ARC Invest is a registered investment advisor focused on investing in disruptive innovation. This podcast is for informational purposes only and should not be relied upon as a basis for investment decisions. It does not constitute, either explicitly or implicitly, any provision of services or products by ARC. All statements made regarding companies or securities are strictly beliefs and points of view held by ARC or podcast guests and are not endorsements or recommendations by ARC to buy, sell, or hold any security. Clients of ARC Investment Management may maintain positions in the securities discussed in this podcast.
Hey everyone, welcome to FYI, ARC's weekly podcast on innovation and technology investing. I'm analyst James Wang. This week, I am speaking with the founder of Nervana Systems, Naveen Rao. Artificial intelligence is obviously my passion, and I follow the hardware industry very closely. And if you recall, in the last couple of years, in the last 5 years or so, we've had over 50 companies be born into this world, dedicated to making artificial intelligence run faster, whether in the data center or on the edge or in cars like Tesla's automobiles. And all this started with NVIDIA's kind of birthing, if you will, of the modern deep learning movement of running artificial intelligence, specifically deep learning, on GPUs. And that created a whole industry. And the first kind of chip company to be born following that renaissance was Nervana. This was the OG company before there was Cerebras, Grok, GraphCore, companies that collectively had soaked up over $2 billion in venture funding. Nervana was acquired by Intel for over $400 million. And Naveen subsequently went on to run the entire AI group at Intel. So what I love about this episode is you really get to see how, as a startup, a company gets created to build AI chips and how the same team of people inside a large organization operate. Intel, of course, is one of the oldest and most successful semiconductor companies in US history. And it's been fascinating to see how such a company responds when a new market like AI gets created. And the backdrop, of course, all this is against NVIDIA, arguably the most dynamic semiconductor company that went from VGA controllers, as Jensen would call it, to programmable GPUs, and now to artificial intelligence processors. This has been an absolute treat of an episode, lots of fantastic nuggets from Naveen on what it's like to compete against NVIDIA and that moment when NVIDIA dropped the Volta GPU, what that did to the whole AI chip industry. I hope you enjoyed the episode. Okay, wonderful. Well, thank you for the time, Naveen. I followed your career pretty much since the days of Nervana, and I know you've been working on AI before that. You actually started off in kind of biology and neurology, if you will. You wanted to learn about the brain and how it has intelligence and gives intelligence. Tell us about your research, how you got started, and maybe the bridge from doing research about human intelligence and then how you started working on machine intelligence.
Yeah, so actually backing up even further than that, and my undergrad, I was EE and CS, like a lot of people in Silicon Valley, and even back then I did some undergraduate research work on neuromorphic systems and intelligent systems. It was always something that was very interesting to me, and even then it was this gulf between what a computer could do on 20 watts of energy and what a human brain can do was pretty large. And it seemed completely intractable. And this is in the 90s. I remember learning about Go and how hard of a computational problem it was. So actually, it was great for me, just as an individual who cares about the space, to see that problem get cracked actually by computers. So I actually graduated, came out to Silicon Valley, worked in Sun Microsystems as a computer architect for about a year. I was going to Stanford at the time and dropped out, went to a startup, which is kind of what you do. Went to several different startups. I actually built chips, ASICs, and software stacks for various problems: video content delivery, video compression, wireless networking, all these kinds of things, which is kind of cool when you're, in a field like chip design. But I always wanted to bring it back to how can we fundamentally change what a computer can do, right? It's not just a thing that does serial tasks. It can actually potentially be intelligent. So I actually quit my job back in 2007, working for a startup called WW Communications that was later acquired by Cavium, and then went and got a PhD in computational neuroscience. So that's where the biology part comes in. And I actually went kind of full bore. I was like, okay, I'm an engineer. I know how computers work. I've designed several of them from ground up. So let me look at what we understand about the brain and see if there's anything I can harvest. Can I take concepts from there and actually apply them to synthetic systems? And so my field of study, computational neuroscience, is really kind of observing data from real behaving animals typically, and interpreting that using machine learning on computational concepts that exist in the brain. How does the brain actually compute a visual signal into motor plans, motor programs, this kind of a thing? So we really think of the brain as some sort of a computer, but obviously trying to figure out how to characterize that in a mathematical way. That was really part of a very long journey. I mean, I'm talking, 25 years or something like that. So, obviously when I did this, my parents and the rest of my family thought I was an idiot, because why would you go back and get a PhD after having a good career, right? As any good Asian parents would say. Oddly enough, the whole field sort of started coming together at that time. And right around then is when deep learning started becoming a thing. I went and took a research position at Qualcomm researching neuromorphic machines. And then it was like, well, clearly this, backpropagation, these kind of methods, which have been around for a long time, are hitting like a stride. There's something now that has come together. The amount of data, the computational power, combined with those techniques, actually allowed us to recapitulate some aspects of intelligence, right? So obviously, this is the area that I've been looking at for a long time. And so then we said, well, we need a better computing substrate for this. The existing computers are not really designed for that kind of problem. And that's kind of where Nervana came from.
Okay. Tell me a little bit about your time at Qualcomm. What was their research division's mandate? How did you pitch yourself to them? And what specific problem were you trying to solve there?
So we were working on a neuromorphic computing, which is really biomimicry in some sense. So the brain neurons use what we call action potentials, or a pulse, to kind of communicate information. So you can communicate a number via rate or by timing of various signals against each other. Obviously that's completely different than two's complement math that we use in a standard logic system. So the research there was, if you represent computation and numbers that way, is there something you can do that's vastly more efficient? And so really it was a bet to say, can Qualcomm leapfrog the rest of the industry by putting research dollars in? And back then, actually, Qualcomm had one of the best sort of AI research groups out there. Not a lot of people know about it. Obviously, Google became huge, but this was before Google even had an enormous group. Qualcomm was doing it probably more tactically for their specific chips and less in a pure research sense. But really, that's what they were trying to crack, is how can we build super low power computing systems that can be intelligent?
Every time I hear neuromorphic, it seems to imply an architecture that's a little different from conventional, I guess, AI accelerators. And it seems to imply algorithms that's not kind of the neural nets that are in production. It's more around spiking neurons and things like that. Did Qualcomm ultimately take that branch in the tech tree and go with something neuromorphically inspired, or did it go with more of a conventional architecture?
Well, eventually it did go to a conventional architecture. And it was interesting because whilst at Qualcomm, it wasn't clear what the right direction was, but I actually kind of pitched some of these ideas internally, like let's build something more for artificial neural networks, not spiking neural networks. And they wanted to continue along the spiking way. And so basically I took that as a no, and that's when we started Nervana. So I guess I should be thankful that they didn't want to pursue that, because that's actually what I pitched internally to do.
That's so funny. Despite your background, you picked a more pragmatic approach.
I did. I'm an engineer in the end, right? I think I played a scientist and I played an engineer. And I think at my heart, I'm actually an engineer. I love to build, but I can be a scientist when I need to be. And so I think really being able to skate between those two things is not something everyone does. I think most people are really one or the other, and they have a very hard time identifying with the other side. So as much as I love the research topic and the science aspect, I knew what was actually practical and what we could really build in a scalable fashion.
How did you create Nervana? Who did you already know you wanted to work with? What role did you take in the company? Did you go in the weeds and design the architecture or write any code? And tell us a little about the fundraising and the environment and reception to a new silicon company.
2014 is when we started. So I kind of got the no from Qualcomm internally to do some of this stuff. And one of the guys I worked with a lot at Qualcomm was Amir Khosrowshahi. And he and I got to talking about it, and he got excited about this. We reached out to his PhD advisor, who's a professor at Berkeley, Bruno Olshausen. We actually had lunch with him over the Christmas break. His family is from Orange County, so we just drove up and talked with him. And he said, yeah, absolutely, you got to go do this. This is the time to do it. With his encouragement, we said, okay, well, let's start that process. And Amir, as you might recognize from his last name, Dara Khosrowshahi, the CEO of Uber, and several of his cousins are actually in the tech world as investors. So he reached out to them and said, hey, what do you think about this? And it was funny because they thought it was like, okay, Amir wants to do this thing, we'll look at it, right? But we went and put together a deck of some slides in a couple of days, and we came to the Bay Area, and his cousin actually ended up setting up a whole bunch of meetings. So one of the first meetings was with him, and he said, yeah, I'll invest in you guys. We're like, oh, I guess we're doing this. I mean, to us, it wasn't even like real yet. We weren't even taking ourselves that seriously, but everyone else was. So we said, okay, I guess we're going to do this. So I was the CEO, Amir was the CTO, and another guy we worked with from Qualcomm that I knew from grad school, I hired him into Qualcomm, came along as the VP of research. And that's when we started reaching out to our networks and started building the team up. We knew we needed to build the chip side of things. I had a pretty deep network there from my previous roles and things like that. And then we started reaching out to the research world, because at that time there weren't really AI people you could just hire, right? It was you had to basically find people who were doing research that was related, bring them in. Someone has good fundamentals around machine learning. We knew we could kind of train them in what we needed. And that proved out to be pretty successful. I mean, we started writing software that was much faster on NVIDIA GPUs. In fact, we had the fastest software. We had 2 or 3 guys who worked on it and beat the entire NVIDIA team. And I think the NVIDIA guys were really like, wow, how did these guys do that? Which is very fun. The new world, a new workload, you can get away with a lot more rough edges, I think.
Yes.
And and then the next part was actually, okay, so we raised a seed round, $600,000 at the beginning of 2014. And then we said, okay, we're going to start doing this for real. Let's actually start building a bigger team. And then that was the hard part. Talking to investors about building hardware and building a hardware platform wasn't so easy. A lot of the investors were burnt by the networking collapses in the early 2000 timeframe, where lots of chip companies came online and all of them lost money. So I don't think most VCs had done a chip investment in nearly 10 years at that point. So when we went to pitch it, most of them were like, yeah, that doesn't make any sense for us. So I think in 1 week, I think I did something like 30 pitches, something like that. It was tiring. Then, we came across some people like Steve Jurvetson. These are guys who actually get this stuff themselves. They understand the details. And in fact, we went back and forth. I was sending him research papers, and he was highlighting things and asking questions. And I'd never interacted with a VC who was like that. And, he got it from the first moment. And in fact, he was like, I've always wanted to do this. I think this is what needs to happen. So from then, he basically wrote a term sheet for us for our first round of like 3.3 million, which again, sounds very small by today's standards, but back then that was a good Series A. And that was enough for us to get going.
3.3 million for how much for the company?
I think our pre-money valuation was 15 million, if I remember right. Yes. So 3.3 over 18.3.
Okay, decent chunk there. I guess that money is what you used to kind of build the first, was it 28 nanometer chip?
Yeah, we had to raise more to do that, obviously. So what we did at that point was actually get all the architecture work done, start really thinking about our business model, actually building what we call a cloud team that was building a cloud API to do training. We were basically going to we were starting with NVIDIA, and then we were going to put our ASIC into the cloud over time. That was the idea. So formulating that whole thing was part of that, really nailing the architecture down and starting to develop open source software like frameworks. In fact, we had one of the first and the fastest framework called Neon that we put out to the world. And this is before TensorFlow and all these kinds of things came out. So that's really where the money went. We subsequently raised another 21 million, which is more for the chip development costs and things like that. But actually, that first year was a lot of fun. Myself, one of the first people who joined the company, Carrie Kloss, Amir, we all sat in a room and actually architected this chip. And it took 4 or 5 years to actually become real. But it was really gratifying for us to see this thing working that we just basically drew on a whiteboard ourselves.
I bet. with that $20 million round, I guess you went to 28 nanometer, got some chips back from fab. How did the initial hardware look when it came back? Did it meet performance expectations? I mean, normally people go through a couple of spins. What's that whole story like?
Yeah, so that was it actually worked fine. We had basically no problems. I think there were time delays though because of the acquisition. So we actually didn't tape out the chip prior to our acquisition with Intel. So the company was started in February of 2014. We were acquired August of 2016. So it was only 2.5 years. We were planning to tape out by the end of that year. Actually, the company had 48 people in it. We were raising another small round just as a security kind of a round because people were throwing money at us at that point.
I forgot to ask, when you were raising the $20 million round, had the atmosphere, which year was it, and had the VC atmosphere changed?
Yes. So 2014 is when we started. May of 2015 is when we closed a $20 million round. And yes, the world had shifted dramatically at that point. Everyone knew what AI was. They knew what neural networks were, and they thought hardware was very, very interesting. And we were the first ones. At that point, it wasn't hard for us to raise money anymore. But we were trying to be diligent about costs and how much dilution we took and things like that. But we did say, hey, let's raise another $5 million round or something like that after we did the 20 million, just so we have some headroom. Because getting money was going to be cheaper, we thought. So the whole point of that was actually to go from 48 people to about 100 by the end of 2016. And we actually got very far with a small team, 48 people building a cloud. We had customers, we had customer enablement, software optimization team, and hardware, all in that original team. But we knew we needed to scale up much more. And so when we started talking with Intel, it was actually around raising a round, getting them in as a partner potentially. We had a couple of other suitors. I probably can't discuss who those are, but you can imagine some of the big tech companies who are out there today in the cloud space were interested.
NVIDIA was never interested.
It's weird. We had a love-hate with relationship with them because we did make their hardware more relevant. We proved 16-bit worked. They didn't. We did it. So we did it on their hardware, right? So our software all ran on NVIDIA. So they loved that. They didn't like that we beat them at optimization. And they didn't like that we were building hardware to compete with them. So we spoke to NVIDIA once, I think, around that time to potentially get an investment. They were sort of lukewarm. We said, okay, forget it. We don't want to give away our secrets or whatever. So we just didn't bother. But yeah, you're right. I've had meetings with Jensen. We had a very cordial relationship. Nothing wrong there. But he clearly thought they could do it themselves, which maybe he was right.
How did the just biz dev turn into we'll buy your company at Intel?
So, we went back and forth with trying to raise a small round of $5 million. That was it. We said, the same kind of thing. We need a lead and all that. And I think by that time, our valuation was around 100 million. Yeah, I can't talk about the other people who were in there in that round, unfortunately. But Intel was going to be a minority investor in that. Then I went to a meeting put on by Allen and Company, who's a small investment bank. And I ended up talking to Wendell Brooks, who was the head of Intel Capital and M&A at Intel. And I told him, like, yeah, we're talking with your guys about a round, but you guys want to take a minority position. He's like, what? No, we should lead this round. I was like, okay, fine. So he made a phone call, and then I get another phone call from Intel. They're like, oh, we want to lead the round. I said, okay. So then Wendell goes back and talks to Brian Krzanich, who's the CEO, and they're like, well, why do you want 5 million? Why don't you take 30? We're like, hang on. That's not what the point of this was. We wanted to keep it small. And then they kept pushing us to take more. So I think we ended up growing the round to about 12 million. They were going to lead it. Then one of the other companies that was going to lead the round before basically said, well, you know what, for us, it's not so interesting to lead a round. We'd rather just acquire you. And so then I had to tell Intel, hey, these other guys who are going to be in the round now want to acquire us. And they're like, well, if they want to do that, we want to do that.
The other guys were already a public, I guess, a large semiconductor company.
They were not a semiconductor.
Oh, they were not a semiconductor.
They do semiconductors, but they're not a semiconductor company. I'll let you figure out which one that might be. So, yeah, then it became a little bit of a competitive thing. It became a roadshow, talked to everybody until kind of went to a bidding sort of a thing. And again, we were like, we did not want to get acquired. We were building a company. And so we had a great position to stand on. We were like, look, we think the future is really bright. You can try to take that off the table if you want, but you got to come in with a serious offer. It's just not worth our time otherwise. That happened in, the negotiations happened middle of 2016, and it closed finally in August. But during that time, we were sort of in due diligence phase with Intel. We couldn't really hire. they asked us not to. And we said, okay, it's fine. Once we get an Intel, we're going to have all these resources available to us. It's going to be great, and we're going to move forward. That turned out to not really be the case. If you recall back then, Intel went through what was called ACT, which was basically a headcount reduction in the middle of 2016. So once we got acquired, we were actually put under a hiring freeze. So it became very difficult, or actually impossible, for us to hit any timelines because we knew we had to grow by 50 people. So 28 nanometer chip would have been fine at that point. This is 2016. We were going head to head with the, I forgot the name of the chip now, the NVIDIA chip, the Maxwell architecture, which is a 28 nanometer chip. And we were going to be more efficient given our architecture was more specific to this. And we had basically tensor cores, right? Those sorts of engines. We were 4 or 5 times more efficient and dense than NVIDIA. So we actually felt we had a good product. But given the delays, it didn't hit the window anymore, right? So we would have probably taped out towards the end of the year of 2016 and had a product in 2017, which would have been fine. When we got an Intel, it was actually quite difficult. As you might have imagined, it's a very large company. We didn't have any budget. We literally had zero budget to grow. And so we were put under a hiring freeze. People started to leave. It was part of my job to try to hold down the fort and continue making progress. The team did actually make progress because people were just passionate. They wanted to see this thing come out, right? So the team worked extremely hard. People still worked like they're in a startup. We had our own separate offices, and they were working on passion at that point. Eventually taped out the chip, I think, in middle of 2017. Through 2016, wasn't so happy. 2017 came along. I've been really trying to fight hard inside of Intel to really be taken seriously. I think the company was in a transition. There was sort of a sentiment that CPUs are going to do everything. It was becoming clear that NVIDIA was the player in the AI space. And Intel was coming to realize that. And then we needed an answer. And so I think I was successful in that Brian Kurzanich came and approached me at the beginning of 2017 and asked if we wanted to start a AI group within the company and if I wanted to lead it. And so that's when things started getting a little more serious. By summer of 2017, we actually had the mandate to do so and could start growing. So it was almost a full year after we were acquired that we could actually start growing. So then it kind of went bonkers, went the opposite direction. It was like, okay, well, we have all these people doing AI related stuff. Naveen, you get to pick who you want to keep, who you want to hire, put together a strategy around this. That was when some interesting fun began, because all of a sudden we had to go from 50 people and we scaled to 500 people in about 8 months internationally, which was probably one of the hardest things I've ever done professionally.
I see. And it seems like your job responsibility had grown in scope. You weren't just in charge of kind of the Nervana folks you came with. You had to kind of create a unified AI strategy across hardware and software for all of Intel. That meant taking on things, I guess, you didn't even, that wasn't your business to begin with.
Exactly, yeah. So we actually had to come up with a software strategy for Xeon. Actually had a lot of influence on the roadmap, which you're seeing now. There's more AI stuff going into Xeon, and the team really drove a lot of that stuff. And then also, of course, the discrete accelerators like the Nervana stuff. So yes, scope grew quite a lot. I was moved out from inside the data center group and reported directly to Brian. And then basically had the mandate to say, okay, here's a group I think is interesting. Let's go talk with them. So these teams are all over the world, Poland, Israel, India, Ireland, all over the place. And so it was quite a lot of work. Like I said, one of the most difficult things, because I still had the mentality of a startup founder where I need to know what people are doing. I need to know what the quality of those people are. I need to know how they work. Because when the group was 50 or 100 people, I knew everybody and I knew what everybody worked on. I wrote the first driver code for the chip, like things like that. Like I need to be intimately involved in the detail. And doing that at scale was very hard, and a lot of learning for me on how you have to let go in the right places,
So it's 2017. You're all of a sudden in 10x ramp for headcount for ambition. By now, NVIDIA had launched Volta, their first chip that had targeted AI from the beginning. How did that change the competitive dynamics, and how did that alter the internal response of like what you guys had to ship?
Yeah, and that's a great question, because it caught us off guard, to be completely honest with you. They announced, I think, in May of 2017, the Tensor Core, the V100. It didn't really become available until December or so, but when they announced that, we said, oh, crap, because we had that advantage. We had that Tensor Core thing, and we thought we still had it. And we figured that NVIDIA would react, but it wasn't going to be to the following generation. Kudos to them, executed like mad, and they deserve it. frankly. Basically, they had to rethink whether we productize the 28 nanometer chip at all. And we decided not to, because with 28 nanometer and the tensor cores against the standard GPU, even at 16 nanometer, we were competitive. A 16 nanometer GPU with tensor cores, we're no longer competitive.
Maybe those who are not super technical, the tensor cores are basically specialized execution units designed for artificial intelligence. NVIDIA had been building GPUs up to this point. They happen to fit neural networks somewhat well. That's why they got their start. But Nervana and later on, countless other AI chip startups build specialized execution units and data paths for neural networks. And NVIDIA basically, I gave a few presentations on this, just kind of when all the chip startups were happening. I basically said with Volta, NVIDIA had shipped the roadmap of all these startups, and that was a big problem.
Yeah, I mean, it wasn't quite as competitive, but they had the software that had been working for years, and all the programmers and the whole development community was around it. So even with 20, 30, 40% less performance, it was going to be more performance, it would be very hard to compete with them. So like I said, that was a huge move from them. And I think that was a defining move for NVIDIA in the AI space.
That's amazing hearing it from the inside. It felt like a pretty major announcement looking at what had happened, what they said back then. But every Jensen announcement is the greatest thing since sliced bread. So you don't know which one is the actual sliced bread and which is just the refresh bread. But this was definitely, they changed the playing field for AI chips.
Yeah, I don't think I've seen a leap anywhere close to that. Even the new stuff, I mean, it's great. They're iterating and they're doing what they've always done, which is, really kind of optimize around what their architecture can do. But that was the big one, because not only was it the tensor cores, it also went to low precision, which is, again, something we spearheaded, and they took it seriously.
Yeah. Basically, I think the three key features that were supposed to be classic GPUs were the tensor cores, the half precision, and the HBM and the architecture that wired all the chips together. And they shipped all of that in one go, basically.
They really did. Yeah. I mean, I think someone I saw on Twitter around that time, they said NVIDIA just shipped Nervana before Nervana did. And that hurt. It was not false.
NVIDIA shipped Volta. What was the new game plan at Intel? And then how did it pan out from there?
Well, now that we were Intel, we figured, hey, we can build relationships with some of the large cloud providers and build the right thing going forward. And, basically we retooled and we said, okay, we're going to get to a 16 nanometer product as quickly as possible. If you recall back then, we actually had an alternative numeric format we called FlexPoint that we had shown to work. It's also, now that NVIDIA shipped the tensor core, basically that caused everyone to standardize around FP16. So that hurt us, right? And it was, again, a great move from them. We already were down a path on the architecture with FlexPoint, and so we had to shift and change. And we didn't do that until a little bit later because, it was kind of a trade-off between we can go as fast as possible to 16 nanometer, get a product out with FlexPoint. If we ship, it's going to cost us 6 months. And so we sort of went down the path, taped out the chip, and we said, okay, we're going to have to switch. And so we went with the B-Float 16. And so basically, that product didn't come out until end of 2018 on 16 nanometer. And it is competitive, and we actually did have customers on it. At that point, we actually had a very good handle on things, which went into 2019, et cetera, et cetera. But follow-on products on 7 nanometer and others were going to be actually very competitive. But the challenge then was really going to be around software, community, and developer tools, that kind of stuff. But on the hardware, we actually had something that was going to be, from the physics and specs standpoint, more in every direction. More I/O, more memory bandwidth, more compute, more memory.
For the training or for the inference part?
Well, for both, actually. So then we actually split the line, and we developed two separate paths, one for inference, one for training. Actually, on the inference side, the product we called Spring Hill was actually trying to find pieces inside of Intel that we could bring together as quickly as possible, go from a concept to a product in a year, which inside of Intel was just unheard of. They didn't work that way. So it was really kind of tough. Again, a sort of an army of the willing. Had a wonderful team in Israel that I brought in from that process where we're bringing people together. And they had an architecture, and we said, okay, how can we build a product around this? Well, in the inference space, CPUs were king. And so let's build something that actually has a CPU, leverages that programming model, and then tacks on low power engines that make it very efficient and fast, low latency. And so that's what Spring Hill was. It actually had CPU cores, Sunny Cove cores on the chip, a big memory cache on chip, SRAM cache, LPDDR, so it was low power, and then highly specialized cores for doing the inference side.
You had made a lot of progress, you were retooled, but in the end, Intel seemed to have decided at some point that they were talking to another startup in Israel called Habana, and then they ended up acquiring Habana, and that has now become the Intel de facto hardware roadmap. Were you involved in that process? Were you pro or against that move? What was that internal discussion like?
Before I comment on that, I think patience is extremely important in these. And I think one of the things that Jensen has done very well has actually been betting on his team and being patient, getting developers to adopt new tools, new architectures, and things like that is hard. It takes time. That's been something that was a bit of a challenge inside of Intel. And really, we had the products coming out. We really just needed the time to let them flourish. I think some people got enamored with the claims of a smaller company. Having come from a smaller company, I know what those claims are about. I know where they fall down. And I think that's the challenge here is like you have to really kind of align against reality. What's really going to ship? What's really going to hit a certain timeline, a certain window? So I was not for the acquisition. It was something that I actually fought actively. That being said, I had to do my job as well. When I was overruled in that, I did what I needed to do, and I tried to take care of my team and see what we could do together and come up with the best possible roadmap. And I think what Intel has done now is try to integrate those things. So a lot of the IP that was developed, obviously in product lines like CPU and things like that, are going forward. In the Nervana accelerators, the product line is not going forward, but many of the concepts, software, and the teams that we put together do continue to live on. So really, that became my job at that point. It was kind of how can we try to make these different elements successful.
I remember. I track these startups for a while. That was my job, kind of just to see what's happening with each of these startups. I just remember when Habana came out, they didn't say much. They put out a bunch of performance charts. They said, no, nothing, just real performance. And I tried to talk to them, and in typical that kind of fashion, they never even responded. That happens with a lot of Israeli companies for some reason. And I saw them at trade shows, but it just struck me as, like, architecturally, I could not tell. What they'd built seemed, roughly speaking, the same kind of ideas as what a dozen other AI chip startups were doing. What was the perceived merit of what they had built versus what Intel understood internally what Nervana the internal chip was building?
Yeah, it came down to execution. There was a perception that they were executing, which they were. For a small team, they executed very well, no doubt.
Well, you were executing well when you were a small team. It's like the second you get brought in.
So yes, that is absolutely true. And I think the challenge comes when, Intel has a highly distributed workforce. That presents challenges. Building a new team, getting a new culture, getting all that stuff up and running takes time. And if you really are serious about an effort, it's 5, 6, 7 years to really get to a point where these groups are going. And, we were only at it for 2.5 at the time. So we were just hitting a stride, I think, at that point. As I said, the Habana team came in and they can take advantage of what the team is able to do now.
Don't they have to throw, like, you had built software for Nervana to work and that to integrate with the Intel stack. Isn't this another stack for Intel to integrate into their whole software offering?
It is. I think the higher levels of the stack are somewhat generic. They care less. They can be built on top of NVIDIA or whatever. So I think those things can work on any hardware platform, including Xeon. And then the specifics of optimization and libraries and programming, the actual chip, that stuff had to obviously be integrated. That's a new part of the stack. And I think that's something that's, if you want to shift product strategy in the middle, that's a difficulty. It's hard to do that. So that was a sort of a hidden cost, call it.
In the while you were experiencing this huge journey, 50 plus startups sprouted everywhere in AI hardware land. They were getting funded billions of dollars. If Silicon Valley became about silicon again for a few years, and now it's not. That was brief. What is your impression of these companies? Do you think any of them are truly special? Do you think some of them will succeed?
So I think what was great about this was that it was all of a sudden a time to experiment again. And frankly, I think that's what makes Silicon Valley great, is the ability to get some smart people in a room with a whiteboard and come up with something in a way that no one else had ever thought about. That's the story from the very beginning of Silicon Valley. We did that in Nervana, and I think some of these teams did that. And to answer your question, I do think some of them are special. So some of them have taken approaches that are analog, for instance. It's hard. Analog circuits, making that stuff work, programming it and all of that, really hard. But it might be worthwhile. There are people doing things in the optics space, optical computing, free space optics. All of that stuff happened because hardware became cool again. So that stuff could yield another like paradigm shift. I think those are all examples of things that fall into that category of what makes Silicon Valley great. Now, kind of jumping on a bandwagon and trying to do it better. I guess maybe that's Silicon Valley 2.0. I don't know, but that's less interesting to me. I think that's what big companies can try to do. Take concepts from smaller groups, either buy that group or imitate it, and then execute like hell. That's perfectly fine as a strategy, but that's not what gets me as a technologist excited. So I think a number of those companies were flush with cash from the very beginning and tried some concepts like that. I mean, companies like Cerebras tried to take a new take, this massive packaging thing, right? Companies like GraphCore tried to take a new take. Let's not have memory interfaces, do everything distributed. Those guys, I think, do fall in this category of trying to do something new and interesting. Whether it works or not, I don't know. But they did try to innovate. And that's what I think was the best part of all of this, was just seeing all the smart people try to throw their best at it.
All of them on paper should have better performance than NVIDIA by a lot. NVIDIA, of course, put in the Tensor cores. They've made a lot of optimizations, and they're now on their second generation Tensor core. But I think, at first people talked about hardware. In the last 18 months, I think people really understood that software is the key here. What does that actually mean? Like, I come from the world of GPUs. I mean, I was originally into GPUs and gaming, and software for that meant, there's a driver that interprets Direct3D or OpenGL, and then that goes to the game logic. There's a team at NVIDIA whose whole job it is to write application-specific profiles at a game level. And, to me, I understand that as like, that's not obvious from looking at it from the outside. The outside, you just think, oh, well, you have a Direct3D driver, so it should work. But to get really performant, you go down to the application level code and you make it work, right? Like, what is it like for neural networks? Is there some person, is it the same level of granularity? Are you writing an optimization for ResNet 50 or a different layer, the 100-layer version of that? What is the work involved in software, and why is it so complicated?
At this point in time, it's not clear that there is one neural network architecture that will work. It keeps changing and shifting, right? We went convnets, or actually first what we call multi-layer perceptrons were the thing. Then it became convnets. That stood around for a long time. Convnets still work for visual applications, but then things like transformers, recurrent neural networks, LSTMs, all of these things have slightly different structures. And in order to optimize those things and make them run in a way that's practically fast enough. What I mean by that is that you could actually train a neural network of that architecture in a reasonable amount of time. It takes optimization on your given platform, on your hardware platform, and you need the tools in order to do that. And so that's what people really mean by the software is a problem. So NVIDIA invested in CUDA and that whole community and programming landscape starting in 2005, I believe. I think at that time it was interesting because it was sort of a shot in the dark. It was like, well, here's a way to make a GPU relevant. I actually don't think it was done with a lot of foresight other than we need to be more relevant in the general computing space. Turns out that investment was leveraged really well for AI because all of a sudden you needed people who needed that performance, needed to be able to move bits from a memory at a precise time to a computing element. And lo and behold, many of the tools were present inside of CUDA. Now, that being said, most AI researchers don't use the full span of tools for CUDA. That's much more general than what the AI world really needs. But what we've seen so far is that NVIDIA has really adopted and adapted the CUDA world to AI and AI researchers and made it easy for them. And then you have Google and others coming on board with all their software tools to provide a not comprehensive set, but a set of tools that now AI researchers can use. I think there's still a lot of work that needs to go into that. I don't actually think the CUDA is the right abstraction for AI, but it was the best we had. I think what's killed a lot of these hardware companies and AI is really that you can go and hand tune something if you know the architecture really well and get high performance. But to achieve high performance on, say, an arbitrary neural network that a researcher might want to go and pursue takes a lot of time. and a lot of ramp up to get there. And once that happens, then you say, well, what would be my performance if I did put 6 months of software engineering time into this? Like, oh, it'll be 50% better than NVIDIA. And said, well, it's not worth it, right? So then they just go and do it on NVIDIA. That's what ended up happening with a lot of these guys. So that's why I mean, you really had to have something that was well beyond what a GPU could do to make it worth the while of the software and research community.
What is the critical piece of software from the hardware company's perspective? I mean, I hear about the graph compiler. Like, is it a single piece in there somewhere that needs to happen? And do you need to tune it per neural network architectural type?
Yeah, I mean, what we're getting to now is a set of motifs. So you can break down neural networks into linear algebra and lookup tables and things like that. And we're getting better and better at that. And so embedding those motifs into a graph compiler, where basically an execution graph is a set of operations down to some granularity. And so you can break those things all the way down to scalar operations, where you can even break down a matrix multiplication and scalar operations. But once you do that, you sort of lose the ability to write an optimized kernel for that operation. So basically, it's finding that right level of abstraction where this is a high enough level of abstraction that a data scientist can sort of think of it and say, okay, give me a fast matrix multiplier, whatever. And then having the person who knows the architecture of the hardware and can write a software kernel that really goes and optimizes that. That's the key. And I would say CUDA was a little bit too far down. They sort of had built it up a little bit, and the framework community was too far up. And so we're kind of finding that balance right now. But again, that's not a great abstraction for a data scientist. They don't want to think about that. They don't want to think about, how do I write my backprop algorithm? What they really care about is, okay, here's my architecture of the neural network. Go and infer the differentiation mechanism and just go run it with and optimize it on my hardware. And if you don't have enough memory, go and spread it over 10 different chips. I don't want to think about how you do it. That level of abstraction is still very, very hard, and we don't yet have it. And I think that's an area of growth, and actually I think it's an area of investment right now for a lot of companies.
Fascinating. What do you think of Google's TPU team? That they kind of built that up on the premise that it kind of around the same time as Nervana, but on the inference side, they were seeing all these voice requests. There were no inference accelerators at the time, so they figured they have to build it on their own. But now there are, presumably dozens that they can pick from, NVIDIA, Intel, startups. They're still continuing with that effort. Now it does training. Do you think it makes sense? Does it make sense for them to do such a thing economically and strategically?
I mean, I think there'll come a point where it doesn't. Again, when they started right around the same time we did at Nervana. I mean, maybe 6 months earlier, something like that. So at the time, it made a ton of sense because you're burning, a ton of energy on these computations that they could just build a chip to go do. As the gap between an ASIC, for these particular operations and a computing element like a GPU narrows, then obviously that economic case starts to erode. At this point in time, I still think Google has a pretty distinct advantage on the inference side, just because they can build something that hooks into their infrastructure and their management tools and all of that kind of stuff. And they don't have to be slowed down by putting a feature request into another company. They can do it themselves. So I think that's the operational benefit for them. On the training side, they were able to do things on distributed computing before anyone else was, because again, they could move at the speed of themselves. They don't need to qualify a part at a certain defects per million or whatever that you do if you're a vendor of silicon, right? When I sell a chip, I have to guarantee it. But if I'm using it in my own data center, I can say, well, screw it, I'll just go replace that rack or whatever. I can come up with my own metrics that are important to me. I don't have to care about another customer. So I think that's where the advantage comes. I think several other companies are trying to do that. They're all going to realize how hard it really is, and to maintain the programming environments and stuff like that, it's going to be expensive. When I started hearing about every large tech player building their own chip back in maybe 2017 timeframe, I basically said, give it 5 years. In 5 years, they'll give up, and there'll be one or two still standing. Google very well might be that one because of their really specific needs and the way they do things.
You've spoken very, I'd say, complimentarily of NVIDIA despite competing against them for a number of years. You've made some pretty big bets recently. They acquired Mellanox for about $7 billion, and now they're in the process of acquiring ARM for about 40. They're historically not a hugely acquisitive company off the $1 billion scale. What do you think of these acquisitions? I guess, what is your read on where they're trying to get to?
Well, I mean, what I think of them, I thought both of them made a lot of sense. Mellanox to me seemed like a no-brainer. Basically, they want to own. They're thinking of everything in terms of AI, right? They're seeing that as the growth of compute for their sort of compute in the data center. And the next big difficult thing is integration of interconnect technologies, right? And doing it in the right way. It has to be modular enough that large players can use it and tack on their own encryption steps to that and whatnot, but have something that already has an install base that they can plug into. So Mellanox just made a ton of sense to me for them. I mean, HPC, who cares about that? I always thought that was a tiny offshoot market, but the rest of the enterprise, they want this, they need it. And so that was clear. ARM is an interesting one to me. I think a lot of people, I've heard a lot of people like on the Twitterverse and whatnot say like, oh, they're just going to kill the licensing business and whatnot. I don't think they will. I think they should go and continue the licensing business because they have a community now. And what I think is the most interesting thing about ARM is that they can invest, NVIDIA can now invest in the software community around ARM. And they're going to continue to grow that with everyone who licenses ARM. They're going to continue to grow the developer community on ARM. And if they invest in it being an AI architecture that maybe is a front end to parallel architectures like the GPU, I mean, it's huge. If they can really make that the front end architecture for networking in the data center and various types of dense compute, it's going to be very hard for other companies to compete with them. And I think that's what their plan is.
NVIDIA's market cap based on kind of these moves and their overall growth is now larger than Intel's. Do you think that makes sense?
It's an interesting one because it from the pure numbers, no, it just never made sense. I mean, Intel, the revenues are on the order of 72 billion a year. And I think NVIDIA's are probably 16, something like that. So even with a massive growth rate, right, 100% year on year, it's still going to take some time for NVIDIA to reach that. So I think there's a lot of overzealous investors out there who are kind of betting on a time horizon that they don't understand, frankly. That being said, I do think they're justified in being very close to Intel because right now, I mean, with the moves they've made, they could steal a lot of share from what Intel's doing. And I think I'm out of Intel now. I don't know the roadmaps and everything that are going to be coming out. And so I think if Intel doesn't react well enough to actually maintain the markets they have, NVIDIA is going to eat at them. And that's what they're going to do with ARM. And that's really going to be painful. And I think in 10 years' time, you might look back and say, well, maybe that was justified. So that's why I hedge my words a little bit and say maybe that $300 billion market cap is justified right now. But it does feel like it's just inflated to me.
Yeah, I feel you. I mean, partly it's just we've been watching these numbers for so long. It's burned into our minds what they quote unquote should be. And also, this is a relative metric. Intel has been punished recently. It's not comparing against Intel in its peak. It's comparing against Intel with this huge narrative overhang of manufacturing issues, AMD competition, and of course, the CEO transition that happened a few years back. Does Intel's one narrative, I guess, right now is just ARM going hardcore into the data center? They're already doing that with NVIDIA. Canon and GPU integration, they could go even harder. How durable is Intel's business in the data center? Like how much maybe invisible stuff or moat that you can't quite see is protecting that business?
I actually think it's quite defensible for Intel, frankly. And this is one thing I think the investors aren't getting is how hard it really is to get the data center, CPU market. There's a lot that goes into an Intel CPU to make it work in the data center. A lot of testing, a lot of legacy software that has worked for many years. I mean, if you think about it, the reason that we can now build data centers with millions of nodes in it is because of the hundreds of billions of dollars of software investment that have gone in over the last 25 years that deal with errors and failures and things like that to actually make it work. When I go to a website, it works flawlessly because there's software that knows how to deal with those errors. When you change those kind of errors and you change the way it's reported, all of that breaks. It's not so simple to make it work. So I actually think Intel has a very strong position there. Obviously, AMD has a similar position with the fact they have x86 chips, but I still think its gold standard is Intel Xeon. Now, this is what I was getting at with that investment that NVIDIA can now make. If they really start investing in the right tools to start chipping away at that, they could have a very strong story in a number of years. But it's not going to happen overnight. I mean, I think Google has flirted with building their own server chips based on ARM for many years. It hasn't really happened because of these issues. Qualcomm, when it was going to go into the server business, they pulled the plug on that. I was actually surprised because I thought they were going to be a player here. They know ARM very well. They have scale. They have low power design. It's not a simple thing to break into. And even with an x86 chip, arguably with better performance or better cost or whatever, AMD's not taking share away like, hand over fist. It's a slow thing.
Yeah, I definitely agree. I think seeing AMD's progress for instruction set compatibility, everything being compatible, it's still not just as easy as per dollar per watt is better. I buy you. It's just there are many considerations.
There are.
You are now out of Intel. Tell us about what you're doing now. What is capturing your interest? I see that you're helping at the Allen Institute. I'm guessing if you were to start a new company, it's not going to be a chip company. Maybe I'm assuming too much. What do you think is worth doing in AI, or maybe your other interests circa 2020?
Yeah, so I actually have been investing in various startups and advising various startups for years, actually while I was in Intel as well. And I've kind of leaned into some of those a little bit more, helping them raise rounds, advising them on strategy, just, basically applying what I've learned over the last several years. And some of them are chip companies. So I think there are some opportunities still in the chip space. And I would say it's more around the product side, how you put these features together in the right way to solve real problems. So I think that's a lot of fun for me. Also, I love the science world. The Allen Institute is, I get to, kind of get my science jollies as well as give to that community a bit. And so I advise them on I'm on the scientific advisory board as well as a technical advisory council, which is like how they do infrastructure and things. And then also I review for various journals like NeurIPS and ICOR. So that's kind of what I've been doing. I think I do have a couple of irons in the fire right now on what I'll be doing going forward. You can bet that it'll be in the AI space. My heart is still really in this very deep technical problem of how can we build true synthetic intelligence, something that's practical, something that runs on 20 watts, something that allows intelligence to proliferate out into the world. It's not just something that lives on a screen. That's kind of really my overall goal. And then finding ways to use that to improve human life. I have the fortunate position to be able to think about those missions and really pursue them now. So the next thing I do will be in those couple of buckets.
That's awesome to hear. I think it's great that Silicon Valley, AI is, the most ambitious software project you could conceive of. And Silicon Valley's been around for many decades, but it's never really it's gone after more practical things. Lofty, but still somewhat practical. This one, in the last 5 years since, deep learning started taking off, we've had multiple people basically make it their mission statement to make artificial general intelligence come true, right? We've had OpenAI in the US, DeepMind in the UK. John Carmack, of Doom and Quake fame, is just a one-person research effort to work on AI. That's really heartening to see. It seems like, it's hard to say, but it seems like we're still missing some understanding both on how the brain does intelligence and, if that is even transferable to machines. I guess, do you think, there's no question in my mind, just applying what we have today to society, that's going to yield great results. But what are the important things that needs to be done, either kind of borderline research or applied research, to get us closer there so that we have some timeline or visibility into something that looks like AGI?
I think we have a fair bit to go, frankly, on how we understand how to learn from data. Our interplay between priors that are sort of structurally embedded into a network and what's learned and tweaked, it's still not well understood. Just from a philosophical standpoint, science has gone through many different versions. There was one time where everybody thought, your lineage is derived from the king, therefore you're something special, to kind of swinging completely the other way and saying everyone is the same, everyone's a blank slate and can learn everything. And so I don't think either of those things are true. I think priors and sort of genetic wars actually do help refine the system and actually make it work well for certain kinds of problems. We don't yet understand that. And we don't really have a way for AIs to evolve and change and fit different niches, right? We sort of have to say, I want to build an AI to do this. And what we're all looking for is this sort of magic algorithm that just does it all. And I don't think there is such a thing. I think the brain actually utilizes many different kinds of learning and algorithms. I mean, some of them come up by chance, some of them are from our environment. But like just looking at the way our genome gets tweaked and evolved and sometimes works allows us to explore all kinds of different parts of the space, and then building a system from that system that itself evolves that knows how to evolve in a given niche that it's in is something we just don't know how to do. So I don't think it's going to be this magical moment where we discover a new algorithm and it's going to be intelligent. It's going to be a slow progression toward greater and greater generality for systems. And I think that's actually part of what I want to crack is obviously not the whole problem. That's too hard. But what can we do that can really start to say, well, can I put different types of learning together to make them learn overall more effectively? Some kinds of learning actually work for certain problems. Optimization theory works on certain problems. Sort of Bayesian search and other kinds of things work in other problems. Can we combine those in interesting ways to actually improve the whole system? And I think that's kind of the way I'm thinking about the path forward is take the bag of tricks we have and start applying it in new ways and then pushing the whole field forward.
That sounds very similar to kind of Domingos' book, The Master Algorithm. He was talking about combining different schools of AI and forming something that's more unified.
Yeah, I know, Pedro. It's true. We agree on that. I just think everyone took his book very literally in the title and said he was suggesting this master algorithm. It's like, no, he really wasn't. I think he's suggesting that there is a master algorithm, right? So I told him it's not well named.
Well, he seemed to have sold a good number of units. So.
That's right.
Well, Naveen, thank you so much for the conversation today. I've learned so much, and it was great to hear your candid account of really doing the first AI chip startup. And that was a very inspiring effort. Thank you.
Absolutely. Thank you for having me. A lot of fun.
ARC believes that the information presented is accurate and was obtained from sources that ARC believes to be reliable. However, ARC does not guarantee the accuracy or completeness of any information, and such information may be subject to change without notice from ARC. Historical results are not indications of future results. Certain of the statements contained in this podcast may be statements of future expectations and other forward-looking statements that are based on ARC's current views and assumptions, and involve known and unknown risks and uncertainties that could cause actual results, performance, or events to differ materially from those expressed or implied in such statements.